Lesson 3.6, we're going to look at linear systems with three variables. And so far, we've just usually had an x and a y, but now we have an x and a y and a z, or ABC, or whatever it might be. But when we graph an equation with two variables, we get lines, or a line. Three variables, we get a plane. Here's an applet that you could look at to see different planes and the equations for those planes. But here's the type of systems we can get when doing three equations with three variables. This is oftentimes what we get. We get one solution where the three planes intersect at one point, and those are in the examples we do. There's obviously many other things that can happen with three planes. Each of these systems would give no solution. So here you have all the planes are parallel, so there's no intersection at all. Here you have two planes are parallel, and then the one cuts through, and then here you just see how they're all at different angles and don't ever intersect at a point. And then here's an infinite number solutions, just a couple examples. Here's where three planes intersect, and they intersect at a line. And then this one is trying to show that there's three planes that actually end up being the same plane. So let's go ahead and jump into this. We can use both elimination or substitution method here. I have addition, but this is elimination. Some things say different things, so elimination method or substitution. So group two pairs of equations and use, and we don't always have to do this depending on how it's set up, but we want to use elimination or substitution to eliminate the same variable in each pair. In the second example we'll do today, we actually have some equations with only two variables to start with, so we don't necessarily have to do it twice, but we will have to do it twice here. The key here is to eliminate the same variable in each pair, and that's what we'll do. So once you do that, you're going to do it twice. You're going to have two results that have two variables in them, and then you can do a substitution or elimination to solve the system. Once you know those two, you can plug two answers back into one of these original three equations to find the third variable. So we're going to jump right into this. Remember, there are more convenient ways to do elimination, so we want to look for what's best. The way I do it this way, so in this case, I'll just tell you we're going to eliminate y to start with. It's not always y that's the easiest, and in fact in this one you could eliminate z or you can eliminate the x's, but in this case y is set up really nicely to eliminate twice. So what I'm going to do, I notice that here I have a positive y and a negative y, so if I group those together, so I'm going to do x plus y minus 2z equals -9, and then the second equation, 3x minus y plus z equals 13. If I group those and add them together, I didn't even need to multiply top or bottom by anything, or either of these by anything, because the y's just eliminate. So I'm going to add these together. I get 4x. Y's eliminate. -2z and z is -z equals -9 and 13 is 4. So I grouped those two and got 4x minus z is 4. Now, how can I eliminate y again? Well, I could use first and third equation and subtract, or actually second and third is going to work well because we have a negative and a positive. So I'm going to write 3x minus y plus z equals 13, the second equation, and then the third equation. And we're going to add those together because these will eliminate here, and we get 5x plus 5z equals 30. Actually, looking at this, we notice that everything is divisible by 5. So I'm going to quick divide everything by 5 just to make this a simpler equation with smaller coefficients. So dividing both sides by 5 or dividing each term by 5 gives us x plus z equals 6. That doesn't always happen. In fact, it didn't happen here. We couldn't divide everything by the same number to get smaller integers. So now we have two equations. So we grouped two pairs of equations and used elimination to eliminate the same variable. We eliminated y here and we eliminated y here. That's not to say we always have to eliminate y's. Some problems in your homework that you get, you might be easier to eliminate x's. So now we're going to pair up the results from step 1. So I'm going to take 4x minus z equals 4 and x plus z equals 6, and I'm going to pair those together, and now I'm going to use substitution or elimination here. Well, this one's set up easily for elimination again. They're not going to all turn out like this, but we didn't have to multiply these by anything. So we're going to add those together. We get 5x, the z's eliminated, equals 10. So divide both sides by 5, x equals 2. So we have part of our answer, and now we're going to work our way back, and we can use one of these two equations to find z. This one looks like it will be easiest. So we're going to do x. So x plus z equals 6. Well, we just found x is equal to 2. So 2 plus z equals 6. Subtract 2 from both sides. We get z equals 4. And so we just solved this system of equations. X is 2, z is 4, but we need to find out what y is. So we're going to take x equals 2 and z equals 4 and put them into any of these three. Doesn't matter which one. I'm going to choose the top one. Looks pretty easy for us, so I'm going to write this out. Again, you could use the second equation or the third equation. And we know x was equal to 2. We're trying to find y, so we leave that in there. Minus 2 times z, which was 4, equals negative 9. This is negative 8 right here, so 2 plus y minus 8 equals negative 9. 2 and negative 8 is negative 6. And add 6 to both sides, and we get negative 3. So as long as we did everything correctly, our answer is 2, negative 3, 4. Instead of having an ordered pair like we did for with a system with two variables and two equations, we would have an x and y. Now we have an ordered triple, x, y, and z. I'm going to go ahead and check this real quickly. We don't always have to do this, but I'm just going to plug them into each of these. So 2, negative 3, 4. So we have 2 plus y, which is negative 3, minus 2 times z, which is 4. And we're checking, does that equal negative 9? Well, this is negative 8, so we have 2 plus negative 3 minus 8 equals negative 9. 2, so this is negative 11 plus 2. So this works. Putting in the next one, again, 2, negative 3, 4. So 3 times 2 minus negative 3 plus 4. We want to know, does that equal 13? This is 6. Minus negative 3 is plus 3. Plus 4. Does that equal 13? 6, 9, 13. Yes. And then checking the last one, 2 times x, which is 2, plus y, which is negative 3, plus 4 times z, and z is 4. Does that equal 17? Coming across, we get 4 plus negative 3 plus 16. Does that equal 17? 4 plus negative 3 is 1, plus 16 is 17. So that is the correct answer. So we see that this ordered triple made all three of these equations true. And so there is our answer for that one. The next one here is set up a little bit differently in that we have three equations and three variables, but each equation only has two variables. And so we still want to get to the idea where we're going to solve two equations with the same two variables. There are several different ways to do this. We could do elimination in a way, but in this case, I think the easiest way is going to use substitution. And I'll show you what I mean here. This has an x and a z, and this has a y and a z. So if we can somehow get this y to have an x in it we can have an x and a z here. And what we're going to do here is start with this first one. We're going to subtract x from both sides. So y equals negative x plus 6. And we can use substitution, and we can plug this in for y. So let's see what that looks like. So we have 3. Let's come down here. 3 times y. Well, we just solved for y, so we know y is negative x plus 6. Minus 2z equals negative 10. Distribute. We can subtract 18 from both sides. These are not like terms. This is an x and this is a z. So we're going to subtract 18 from both sides. And we get negative 3x minus 2z equals negative 28. And so now we have that equation with an x and a z. And from our original set of 3 equations, we have this one. So we have 4x plus 5z equals 56. And now we're down to 2 equations with 2 variables, so let's go ahead and solve this. None of these, like the other one, just kept working out where we could eliminate easily. I'm going to go ahead and eliminate the z's here. So this is a negative 2 and a 5, so the common multiple is 10, so I'm going to multiply the top by not 2. Multiply the top by 5. Which gives negative 15x minus 10z equals 28 times 5 is 140, so negative 140. And then that gave me a negative 10z, so I want to multiply the bottom by 2. And that gives 8x plus 10z equals 116. And we did that so we could eliminate the z's. So those eliminate. We get negative 7x, negative 140, and 116. Sorry, that's 112, not 116. 56 times 2 is 112. Negative 140 and 112 is negative 28. Divide both sides by 7, negative 7, and we get x equals 4. So we have x equals 4. We could do a few different things here. The easiest will be to come up here and find y. So let's do that. So we know x is 4. So I'm using x plus y equals negative 6. 4 plus y, equals positive 6. Subtract 4 from both sides, and you get 2. So we have x is 4, y is 2. We need to find z. We can plug it into either one of these, or we could even plug something in the x value into here. I'm just going to come up to this one, 3y, which is 2, minus 2z equals negative 10. So 6 minus 2z equals negative 10. Subtract 6 from both sides gives us a negative 16 over here on the right. So negative 2z equals negative 16. And dividing both sides by negative 2 gives us z equals 8. So our answer would be x comes first, then y, and then z. Again, what we did before is we could go back and check them and plug in. So 4 plus 2 equals 6. Plug in y and z, so 2 and 8. Put a 2 in here. Just think with me here. 3 times 2 is 6. Minus putting 8 in here. So minus 2 times 8 is 16. 6 minus 16 is negative 10. That works. And then this last one, 4 times x, which was 4, plus 5 times z. Z was 8. And that's 16 plus 40 does equal 56. So it works. Again, you don't always have to check, but it's nice to know if your answer is correct. And that is solving systems with 3 variables.